So indeed, my name is Petri Kannisto, and I work at BFI, or in the full form, the institute is called VDE-Betriebsforschungsinstitut. It is located in Düsseldorf, Germany. I'm working there as a researcher. And the slides were prepared together with my colleague, Andreas Wolf. So for the contents of this part, this digitalization part, there are three main sections, you can say. So step one would be a minimal concept. Then step two, the so-called full concept with more aspects included. And then finally, the ICT viewpoint. So how this is going to be done from the software needs. And my background is more in the ICT part. So I know something about modeling, but let's not a hard expert in this. So if you ask something, then I hope then we can direct the question to Andreas. So for the first concept, so we focus on the control problem with three factors: vapor temperature and moisture, and then as a third factor, energy optimization. So of course, as you optimize the energy part, energy economy, then you don't want to destroy the other measures either. You want to maintain the quality, of course. And related to this, we can perform simulation as well as trials at VTT. For the method part, reinforcement learning will be applied in two steps. So first, a model-free approach, just to understand the properties of the system, and then a model-based approach afterwards with two methods. Internal model control is a relatively robust method, a bit simpler, and then we have model predictive control, either static or dynamic. So static meaning that it focuses on a certain, let's say, certain conditions where it works well, whereas dynamic aims to adapt to various conditions, so to be better applicable in a various range of operating conditions. So for the second step, the so-called full concept, in this figure, the resolution is unfortunately not very good, but you are not supposed to try and grasp, then get the details from this figure anyway. Just to show, this is some simulation model created by Andreas with Modelica. Some of you might already know this tool. So as you can see from the figure, even though it's unclear, there are multiple letters and lines, even colors, to illustrate that there are multiple aspects considered. And this can, of course, be used in control. And it can be exported as a so-called FMU component. So FMU or FMI are standards for co-simulation, or let's say component-based simulation, where you divide your problem into sub-problems, and then you can integrate these together, supported by various environments. And what we actually do here, so besides this nice figure that you just saw, so let's see, there are three main aspects. So of course, normal control. So this is the usual basic operation. We want to control these three measures, so the moisture and temperature of the paper, as well as energy optimization. But and then these remaining two, so B and C, are a bit more specialized. So startup control, step by step, and fault diagnosis. And so, of course, it increases the added value of this concept if you can focus also on something more than only the normal operation. Then thinking about exploiting these technologies in actual production, so you have to think about the capital expenditure. And for this, it is great if you can reuse the heat. And even for this, we have an idea. So we can store the excess heat into an external heat storage, and then it can be reused by heat consumers in the external world. And they have been saying that we could store this as salt, so as chemical energy. And this, like I said, so capital expenditures are going to make more sense, as this will make the solution more profitable if successful. And this is going to be studied as simulation. So as the final part, so the ICT aspects, these are still in a preliminary stage, but there are already discussions. So it seems that a good candidate for the data integration technology here would be MQTT, or message queuing telemetry transport. It is an asynchronous communication approach, provides a so-called message broker. It is loosely coupled, so it means that we don't connect the components directly, but these communicate over a bus, which kind of hides them from each other. It's platform independent and supported widely by various tools, and it's already state of art in the so-called microservices scheme, which is mainstream in many systems these days. But we are of course going to need another technologies as well. So at least any classical HTTP interface for the web for the user interface, and something we still need to discuss to what extent do we want to centralize the functionality and or orchestrate, and to which extent can we distribute pieces of the functionality into various components. For the infrastructure part, we are planning for Docker. So the so-called infrastructure as code, this might be a bit, let's say, a thick concept for those of you who haven't really heard about this earlier. So, but the idea is that you define your infrastructure indeed as a code. So instead of installing everything manually, there is a system that you can tell that I need this platform, I need this component, and then the platform sets is up for you. And this helps the development when the components come from multiple teams, especially. So you can avoid this problem like often that okay, it works in my computer, but now it doesn't work in your computer. So this unifies the environment and facilitates the setup quite a lot. So what's going to happen next in this ICT part? So we are developing a so-called 4+1 architecture view model. So the core idea here is to divide the problem into multiple aspects, because in software world it is just a truth that you cannot usually describe everything in one diagram or with one aspect. So you divide multiple aspects into their own. And this enables you to have a non-ambiguous presentation. We are most likely not going to have so many aspects, but at least 2 or 3 of these 4+1 architecture aspects would already help us quite a lot. So the component diagram you can see on the top, on the bottom left, the sequence diagram for the various interaction sequences on the right, on the top, and finally bottom right, the deployment diagram. So how and where these components actually live. But that's short for the digitalization part. Thank you very much for your patience. And I believe now it's the time to, let's see if there's something that I could reply to. Okay, so it doesn't seem to be directly to me at least.